Now we are going to see GTO, that is gate turn off thyristor. This is the symbol of GTO. Okay, it has anode, cathode and gate. Okay, then this is the structure of the GTO. Actually, here in GTO, it is said to be interdigited, because interdigited means there is heavily doped P plus region with N spots. Okay, for that we are referring it as the interdigited. This also belongs to the thyristor family, but for SCR we need a commutation circuit. We need separate circuit to turn off the SCR. But GTO we don't want anything, that it can turn on and turn off automatically. That is not a problem. Then gate has full control over the GTO. Okay, here you can see that there are P plus, N minus, P plus region, then N plus spots. See here, these are the junctions J1, J2, J3. This N plus and N plus region makes the forms the gate cathode combination. Okay, whenever we are applying positive voltage to the gate, this gate and cathode will be forward biased, and current start and GTO starts conducting. Okay, anode is connected directly to the not directly, anode is connected to the P plus region. Okay, this is the N minus region, is nothing but drift region. You know what will happen in drift region. Here, um, yeah, P plus region is directly connected to the anode. So this is nothing but, this is called anode short. Okay, N minus region is the drift region, that you know that electrons and holes will come and accumulate, will come here, and it will accumulate, it will pair the, it will form the pairs. Okay, then free electrons will get more kinetic energy and it will knock off other atoms to release more and more electrons. So current starts flowing continuously. Now we'll see the VA characteristics of the GTO. VA characteristics. The graph is plotted between the anode cathode voltage and anode cathode current. Okay, this is this from 0 to this VBO is nothing but a makeover voltage. So the graph from 0 to VBO, in this region, the GTO will be in forward blocking mode. Okay, whenever the voltage is greater than VBO, it turns on. Okay, to turn off the GTO, simply by removing the gate drive, we can turn off the GTO. Okay, but in reverse bias mode, it's not it will not, it is not having that reverse blocking mode. Okay, suddenly, because immediately the anode negative current will start increase, so it is not having that reverse blocking mode. Okay, this dotted line, no, that indicates that the GTO can be turned at any time whenever the voltage is greater than VBO, that is forward breakover voltage. Then we'll see the applications of the GTO. They are mainly suitable for low power applications, used in heating and motor drives. They are used in rolling mills, robotics, machine tools, traction device, and inverter drives. Okay, okay. Then we'll see that Triac. Triac means it's nothing but triode. Okay. Then it is used to control AC power supply. So the both the it got the name Triac. Okay. This is the bidirectional device. Okay. It conducts in both the direction. There are it conducts in both the direction. 1 minute. Okay. It has three terminals. One is main terminal 1 and main terminal 2 and gate. Okay, I'll show you the symbol of, yeah, this is the symbol of triode. This is main terminal 1, MT1. This is main terminal 2, MT2. Then this one is gate. Okay, here when MT1 is forward biased, when MT1 is forward biased with respect to MT2, then current flows from MT1 to MT2. When MT2 is forward biased with respect to MT1, current flows from MT2 to MT1. Okay, then it will turn on when the gate drive is applied. The input is AC here. That's why it has got the name Triac. Here, what will happen? Track is triggered in every half cycle because the power is to be controlled in positive as well as negative half cycles. So the track is then triggered in every half cycle. The track turns off when the current falls to zero in every half cycle. Okay. We'll see the VA characteristics of the track. This is the graph plotted between forward current and forward voltage. Okay, this is the from 0 to VBO is the forward breakover voltage. From 0 to VBO, the track is in forward blocking mode. Okay, once the voltage is greater than VBO, breakover voltage, the track turns on. Okay, then it starts conducting. Okay, here track is on, MT2 terminal is positive. Here also track is on, but MT2 terminal is negative because in this graph, from 0 to minus VBO, that is negative reverse breakover voltage. From this point, from 0 to this point, that track will be in reverse blocking mode. Okay, once the voltage increases above reverse breakover voltage, it starts conducting. Okay, this is reverse blocking mode. Once the voltage is greater than a reverse breakover voltage, the track turns on. This dotted line indicates whenever the voltage goes higher than VBO, that is breakover voltage, then the track will be switched on. Okay, this is the structure of the track. Here we are having P2, N1, P1 region. N3 is also there. Okay, MT2 terminal is directly connected to P1. N4 and N2 regions. N4 forms the gate. N2 region is connected with MT1. So here the main thing is the polarity of the applied voltage decides the current flow through these layers. Okay, that's it. Then we'll see the Diac. Diac, the nothing but it is a two terminal but four layer device. Diac is 1 minute. So Diac is the two terminal and four layer device. It is mainly used to trigger the tracks. Okay, the symbol I'll show you in the next page because I can't go back, that's why. Okay, it can be used in any direction. It is low power triggering device. Okay, we'll see the characteristics of the VA characteristics of the diagram. The graph is plotted between current and voltage, like like Triac. This is also having that forward blocking mode. VBO, you know that forward breakover voltage. Whenever the voltage is greater than VBO, it's the diac turns on. Okay. In the same way, it is having reverse blocking mode. Whenever the voltage is greater than minus VBO, that is reverse breakover voltage, the diac turns on. Okay. And when it turns on, the voltage across it drops to the negligible value. Okay, then this from this graph we can come to know that the characteristics in the forward blocking mode and reverse blocking mode in forward bias and reverse bias mode is exactly similar. Okay, application of the DAC, that they are used as a triggering device for Triac in power control circuits, light dimmer, heat control, furnaces motor. See, we'll see the light dimmer just for the example I have given. Light dimmer using Triac DAC. Here, this is a voltage source. Load is connected here. This is the variable resistance. Then capacitor is connected with variable resistance. This is DAC. This is Triac. Okay. When the capacitor voltage exceeds the breakover voltage, okay, sorry, when the breakover voltage of the diac exceeds the, sorry, when the, what is that, when the capacitor voltage exceeds the reverse breakover voltage, it starts conducting. This voltage is applied to the triac and it turns on. Okay, that is the mechanism. So the changing of the capacitor can be controlled by the variable resistor. Okay, that's it. Okay, we'll see the general layout diagram of the firing circuit. This is control circuit, power supply, pulse amplifier, pulse transformer. Okay, this is thyristor. Okay, here here the pulse transformer is served as the isolation circuit. Because the whatever the signal we are getting from the control circuit, no, it is very small, so that needs to be amplified. Okay, so that for that we are using pulse amplifier. But after that again, this firing circuit operate operates at low voltage. uh, Here actually this firing circuit, no, this is called that control circuit, power supply and pulse amplifier is called as firing circuit. The pulse transformer and SCR is known as triggering circuit. Okay. So here the firing circuit operates at very low voltage, that is 5 to 20 volts, but thyristor operates at high volt, greater than 250. So there must be an electrical isolation. So for that we are connecting pulse transformer here. Okay, that's it. This is the general layout diagram of the firing circuit. Next we'll see the OR firing circuit. Okay, OR firing circuit, in that the connections are made as shown in the figure. Here AC supply is given, load is connected with AC supply, then here R minimum is there. Okay, this is the with cross mark resistance with resistor with cross mark indicates variable resistor. Okay, this is RB means stabilizing resistor. Okay, and this is anode, cathode, and this one is diode. Now we'll see what's the, we can walk through this one through the circuit. Okay, if R minimum, which this one is used to limit the gate current to its maximum value. Okay, so R minimum is greater than or equal to Vm by Ig max. Vm means maximum voltage, Ig gate current maximum. Okay, uh, this equation we got, this is based on the Ohm's law. Okay, the resistance Rb is the stabilizing resistance, stabilizing resistor. Okay, this variable resistor, no, R is used to trigger thyristor 1 T1. This R is used to trigger thyristor T1. That if the resistance is very small, then triggering angle will be very small. As we increases the resistance, the triggering also will be increased. The anode cathode current the anode cathode voltage and gate current are in phase. So here one thing we must note that triggering angle cannot be exceed cannot exceed 90 degree. Okay, it can't go beyond that 90 degree. Then why we are using this stabilizing resistor? Stabilizing resistor, no? It will take care that voltage voltage should not exceed minimum gate voltage. Otherwise, that thyristor will turn on. So it should not, the voltage should not exceed the minimum gate voltage. Otherwise, the thyristor will turn on immediately. Okay, for that we are using stabilizing resistance. So here I'm not able to give the graph. Okay, that we'll see later on. Somehow I'll add that also. So this is the OR firing circuit. Okay. Okay. Next we'll see the RC firing circuit. In RC firing circuit, AC supply is given to AC supply is connected to the load and thyristor is connected here. Okay. One variable resistor is connected with the load. Then capacitor is connected here. Here one diode and diode 1 and diode 2 are there. Okay. Actually, the capacitor charges in the negative half cycle. The capacitor charges in the negative half cycle and then discharges through resistance R during the positive half cycle. Okay, it capacitor charges in the negative half cycle and discharges through R in the positive half cycle. In the positive half cycle, the thyristor triggers when the capacitor voltage is greater than the thyristor triggers when the capacitor voltage is greater than VG, minimum gate voltage. When it will be triggered when the capacitor voltage is greater than minimum gate voltage. The diode 1, why we are using diode 1 here? The diode 1 prevents the negative capacitor voltage appearing to the gate. Okay. Negative voltage should not appear at the gate. For that we have to avoid that we are using D1. Here the triggering angle can be 0 to 180 degree. Okay, we'll see the next one. Well, then that RC firing circuit, no, it is called half wave RC firing circuit because the triggering is controlled only in one half cycle of the supply. Then this one is full wave RC firing circuit. Full wave or RC firing circuit. Here the connections are made as shown in the figure. AC supply is connected to the load. Here we are using four diodes D1, D2, D3, D4. Okay. Here thyristor is connected here. One variable resistor is connected, then capacitor is connected. Here the AC supply is given to the thyristor through uncontrolled rectifier. So what will happen? Both the half cycles AC current, no. So both the half cycles are positive half cycles. In both the half cycles, the thyristor will be triggered. Okay, when the capacitor voltage is greater than, in both the half cycles, that the thyristor will be triggered when the capacitor voltage is greater than minimum gate voltage. The thyristor turns on. Okay, when the thyristor turns on, the capacitor's voltage clamped to 0. Then it will wait for other second half cycle. It will wait for another second half cycle. Okay. Here also the firing angle can be varied from 0 to 180 degree. That's why we are controlling in both the half cycles. Okay, so the name has given full wave RC firing circuit. Okay, that's it. Somehow I'll try to add the graph because by seeing the graph you need to explain. I'll do it in the next class. Okay, if you like this video, you please subscribe, share and leave your comments for review. Thank you.